Bismillahirrahmanirrahim. Assalamualaikum. So today we are going to discuss a course Inorganic Material Chemistry. Course code is CAM 3115, and we will discuss topic is properties of advanced materials. And under this topic, properties of advanced materials, today we will discuss dielectric properties. In today's lecture, that is about dielectric properties of advanced material. So before going to further discuss the properties of advanced material, first we will discuss about dielectrics, is introduction of dielectrics, and few examples of dielectrics. And next, there are few terminologies that should be we should understand about that first. That about our that is about dielectrics, and next term that we will discuss about, that is about polarization. When we talk about dielectrics, then we should know about capacitors or capacitance. So next thing that we will discuss is about capacitance and capacitance and permittivity. Then we will derive equation, and we'll see the relation between these two terms. And finally, we will discuss about polarizability and polarization and their equation, how we can use the equation or how we can drive it, and their relationship as well. So first, generally, we will discuss about what are dielectrics and why we need this. So we can say that the amount of charge that is stored in a capacitor is a product of voltage and capacity. So what is capacitor? Capacitor is a device for storing electrical energy, and it consists of two conductors that are in close proximity and insulated from each other. So what thing limits the amount of charge that can be stored on a capacitor? We can say that the voltage can be increased, but electric breakdown will occur if the electric field inside the capacitor become too large. So the capacity can be increased, capacity of capacitors can be increased by expanding the electrodes areas and by reducing the gap between that electrodes. So in general, capacitors that can withstand high voltages have a relatively small capacity. The capacitors that can withstand high voltage have a relatively small capacity. So if only low voltage is needed, however, compact capacitors with rather large capacities can be manufactured. So one method for increasing the capacity of that capacitor is to insert between the conductors and an insulating material that reduces the voltage because of its effect on the electric field. So, method for increasing the capacity of capacitor is to insert an insulator or insulating material between the conductors that can reduce the voltage because of its effect on the electric field. So, such materials which are placed between these conductors are called dielectrics. That dielectrics are substances with no free charges. So further we will discuss about the dielectrics in detail. So a dielectric or dielectric material, we can say that it is an electrical insulator that can be polarized by an applied electric field. When we apply an electric field to an electrical insulator, that material could be polarized. So when we can say that when dielectric material is placed or kept in an electric field, Electric charges do not flow through the material as they flow in electrical conductor. So in electrical conductor, in previous lecture lectures we discussed about electrical conductors, that is the flow of current is due to the flow of charges. But in case of insulator, there is no flow of charges. So only when we apply an electric field, only slightly shift from the average equilibrium position to may occur, and that can cause dielectric polarization. Later we will discuss this by adding some figures. So examples of dielectric materials include, that could be ceramic, or glass is an type of dielectric material, plastics and oxides of various metals, and then can be dielectric materials. And when we add some electric field, then they can be polarized. So few liquids and gases can also function as good dielectric materials. So another example is dry air. Dry air is also an excellent dielectric material, and it is used in different capacitors and in different types of transmission lines. So in case of liquids, distilled water is a good example of dielectric material. So as before we discussed about dielectrics, and we also discussed about capacitors, and now we will go forward for the dielectric properties and polarization. What is polarization, and what is capacitance, what is capacitor, and what is capacitance. So the term insulator is mostly used in case of materials which have low electrical conduction, and dielectric typically concerns, it means materials with a high polarizability. So this polarizability or dielectric is also expressed by a number called relative permittivity. So we can say that the term insulator is generally used to indicate electrical obstruction, while the term dielectric is used to indicate the energy storing capacity of material by means of polarization. So we can say that a common example of dielectric is electrically insulating material between the metallic plates of a capacitor. So the polarization of the dielectric by applied electric field increases the capacitor's surface charge for a given electric field strength. So this dielectric could be used between the metallic plates of a capacitor as an insulating material. So in today's lecture, we will cover the basic aspects of dielectric, and we will discuss that when dimensions or size become small, what are the changes in the dielectric property of the materials. So today's lecture will mainly revolve on the fundamentals of dielectrics and what are the different properties associated with any materials that are related to their dielectric properties. So first we will discuss that what is meant by dielectric, what is dielectric property. So a dielectric is an electrical insulator that could be polarized by the action of applied electric field. This means that in general, dielectric is something which is non-conducting and which has a high resistivity. If material that is non-conducting, that will have a high resistivity, as we discussed previously in electrical properties. So it is like electrical insulator, and this material can be polarized by applying electric field. So we can say that in general, a dielectric is something which is non-conducting and which has high resistivity. So it is like an electrical insulator, and this material can be polarized when it will be polarized when we apply a electric field. In this figure, if you look at the material, that you can see that it has got a positive and negative field or charge associated with the material. If you apply an electric field, then this positive and negative charges can be separated. So this is called a kind of polarization. We can say that that material has been polarized. So this kind of particle, without applying any field, may give you an average polarization, which is 0, whereas when you apply an electric field, there will be a resulting polarization. And when we apply this field, that polarization will be in that direction, and there will be charge separation between them, and you can get this or we can say that when the molecules of dielectric are placed in the electric field, their negatively charged electrons separate slightly from their positively charged cores. So with this separation, we can see it is referred to as polarization, and the molecules acquire an electric dipole moment. So dipole moment is can be calculated by which is a product of that charge and the distance by which these charges are separated. So charge separation here is x, and the amount of charges is q. Then the product of q and x gives rise to dipole moment. As we already discussed about when we discuss about dielectric properties, then we also discuss about capacitors or capacitance, or when we discuss about capacitors, we discuss about dielectric properties. So these are interrelated. So this here we can see that this capacitance is related to the charge which develops at one of the ends, and these ends can be of electrodes. And if we say that there are two electrodes, at one electrode you have a positive charge is developing, and on the other side negative charge is being developed. So the amount of charges, that is capital Q, and this is a potential that you have applied as electric field, or potential electric potential which you applied is a V. So this charge divided by potential gives the capacitance. So a charge can be measured in coulombs. So potential is measured in volts, and coulombs per volts gives you the unit of capacitance, which is Faraday or farad, and this 1 Faraday is equal to equal to 1 coulomb per volt, or we can say that 1 coulomb per volt is equal to Faraday. So in the case when where you suppose that you have these you have two plates, and they are separated by a distance d, that distance that d is small d, that is, and the small d is here the distance between these two plates. So if you apply a potential which is V and area of cross section of this material is A, then the total charge capital, that is capital Q, which is developed on one of these electrodes, is given by this equation, where epsilon naught is called the permittivity of free space and E is of course the electric field, which is equal to the electric potential by the distance. And capital A is the cross-sectional area. So this epsilon naught is permittivity of free space, and that means in this medium right now is a vacuum. So when you calculate this, you can use epsilon naught for any real system where you have a dielectric material. Then this equation will get modified because then you do not have a vacuum inside. Normally epsilon naught and the permittivity of free space is given by this quantity. And this equation, as we already dealt with it, so the capacitance of two parallel plates in vacuum will be C naught or C0. So that is capacitance in vacuum with nothing in between the plates, and is given by this equation, as you can see here. So polarizability, we can define it as it is a relative tendency of charge distribution. That charge distribution could be electron cloud of an atom or a molecule that is distorted from its normal shape when an external electric field is applied. So distortion of electron cloud from its normal shape under an external applied magnetic field is called uh, and its tendency to change that charge distribution, that is called polarizability. So we can write equation for this polarizability as polarizability is equal to small p over E. Here P is the polarization and E is electric field, applied electric field. So this polarization small p is for a single molecule, and we can denote it by capital if there are more number of molecules or atoms. So this polarization is directly proportional to electric field, and polarizability is also directly proportional to applied electric field. So if we are talking about more number of molecules or atoms, then this capital P will be directly proportional to E, and this capital P is for polarization. And if we here we are using two constants, that one is psi E, that is electric susceptibility, and other is epsilon naught, and that is permittivity of free space. So electric susceptibility psi E of dielectric material is a measure of how easily it polarizes in response to an electric field. So as a result, it determines the electric permittivity of material and thus influences many other phenomena in that medium. That could be from capacitance of capacitors to the speed of light.
We know that conductors are characterized by a large number of free charge carriers which move between the atoms of the conductors and also within the volume of the conductors. Metallic conductors have a large number of free electrons. When a metal conductor is placed in an external uniform electric field of strength, say E, we know that charge distribution takes place in the conductor due to the movement of the free charges, and the electrostatic induction occurs in such a way that in equilibrium the electric field strength E' inside the conductor due to the induced charges is equal and opposite to the external field of strength E. Hence, the net electric field inside the conductor is zero, and the conductor is said to be in electrostatic equilibrium. Unlike conductors, dielectrics like rubber are those materials in which there are either practically no free charge carriers or free charges. Dielectrics are electrically non-conducting materials. A dielectric material can be made of either polar molecules or non-polar molecules. Polar molecules are those in which there always exists a separation between the average positions of the negative and positive charges in the molecule, irrespective of whether it is in an external electric field or not. Such a molecule is called a permanent dipole and will possess a permanent dipole moment. Water molecule is one such example of a polar molecule. In a water molecule, the center of the negative charge is at the oxygen ion, since it is the negatively charged ion, and the center of the positive charge is at the midpoint of the line joining the two positively charged hydrogen ions. These average positions of the positive and negative charges act as point charges, and hence the polar molecule behaves as a permanent electric dipole. As such, we can say that all polar molecules like water, hydrogen chloride, etc. behave as permanent electric dipoles. Therefore, even in the absence of an external electric field, such molecules possess a permanent electric dipole moment. Non-polar molecules are those which do not possess a permanent dipole moment like the polar molecules. Hydrogen and carbon dioxide molecules are examples of such non-polar molecules. In such molecules, the average centers of the positive and negative charges coincide. Hence, they do not possess an electric dipole moment in the absence of external electric field. Now let us see what happens when a dielectric with non-polar molecules is placed in an external uniform electric field of strength E. Due to this uniform external electric field, the positive charges in the molecules are displaced in the direction of the electric field, and the negative charges in them are displaced in the opposite direction of the electric field. Therefore, in the dielectric with non-polar molecules, the molecules now possess some induced electric dipole moment, and it is said to be polarized due to the external electric field. Now let us consider the case when the dielectric material is made of polar molecules. In the absence of the external electric field E, the polar molecules in the dielectric are such that their electric dipole moments are randomly oriented due to thermal agitation, and hence the total dipole moment is zero. Now when they are placed in the uniform electric field of strength E, we know that every dipole in it experiences a torque, which rotates the dipoles in such a way that they align in the direction of the electric field. Thus, the dielectric material with the polar molecules is said to be polarized. The degree of alignment of the dipoles with the external electric field direction depends on the temperature and also on the external electric field strength. In general, the alignment increases with increasing electric field strength and also with decreasing temperature. Thus, we observe that the dielectric material is polarized irrespective of whether it is made of polar or non-polar molecules, and they develop a net electric dipole moment in the presence of an external electric field. Linear isotropic dielectrics are those in which the induced dipole moment is in the direction of the external electric field and is proportional to the external electric field strength. Now, when this linear isotropic dielectric is placed in a uniform electric field of strength E, it gets polarized. Let us consider the polarization P of such materials, which is defined as the electric dipole moment per unit volume. For linear isotropic dielectric materials in a uniform external electric field, the polarization P is equal to psi E into E, where psi E is the electric susceptibility of the material. Now, each small volume element of the linear isotropic dielectric having a volume dV has a net polarization equal to P dV due to all the dipoles in it in the direction of uniform electric field. Here, it is important to note that the net charge in each volume element will be zero. The resultant effect in the material due to the uniform external electric field will be the formation of an induced positive charge density plus sigma induced on the right face of the dielectric, and minus sigma induced on the left side of the dielectric. This in turn causes a weak electric field of strength E' to be induced in a direction opposite to that of the uniform electric field of strength E. Therefore, the net electric field E0 in the dielectric will be equal to E minus E'. Thus we observe that the polarization effect causes a decrease in the net electric field within the dielectric. Dielectric materials, being non-conducting, are useful in many devices like capacitors, transformers, etc. because of their inherent properties.